Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss about certain circuits which are based on time. So these circuits are called time-based generator circuits. They provide outputs based linearly with respect to time. Yes, we have different types of time-based generator circuits, voltage time-based generator circuits, current time-based generator circuits. Yes, a voltage time-based generator circuit. This a time-based generator that provides an output voltage waveform that varies linearly with time is called voltage time-based generator. A current time-based generator circuit is one which generates an output current waveform that varies linearly with the time. Yes, so we have different examples for them. Yes, we have free running time-based generator. Periodic output is obtained in this. Yes, in free running time-based generator, periodic output is obtained. Second one, in trigger time-based generator, linear output is obtained. Linear output is obtained for a specific duration. I repeat again, in time-based generator circuits, we have voltage time-based generator and current time-based generator. So these are depending on the voltage variation and current variation linearly with respect to time. So there are different types, out of which we'll be discussing free running time-based generator, bootstrap sweep circuit. Yes, free running time-based generator. The input signal is connected across. The input signal is connected in series with the input resistance R1. A parallel branch R and C is connected across the output. Yes, a constant plus VCC is supplied. Base, collector and emitter R2. As soon as VCC supply is given, current I1 flows into the circuit and helps in charging the capacitor by applying a positive going voltage pulse. A positive going voltage pulse like this in the input terminal. Transistor Q turns on to saturation and the capacitor rapidly discharges through the transistor and R1 to obtain VCE saturation. I will be drawing the waveform now. Yes, when an input voltage, a positive going pulse is given to the input of the transistor, the capacitor discharges. Yes. And then charges until it receives positive pulse. Again, as soon as it receives pulse, getting a waveform like this. Yes, so this is the output realized across the capacitor. So This behaves as the pulse width for turning on the transistor, and by charging and discharging of the capacitor, we obtain a waveform as shown in the output voltage. So here, when the input pulse ends, the switch Q turns off and the capacitor starts charging and continues to charge until it receives the next input pulse. Yes, this is free running time-based generator. The next circuit is bootstrap sweep circuit. So we will be trying to get a sweep waveform R1, R2, voltage divided by a circuit fed to the base of a transistor is through the help of a diode and a resistor connected to the collector terminal. The capacitor is connected to the output is across the collector terminal. Capacitor is connected in the output through a resistor R4. Yes, R4 resistor, V0 output, Q2 transistor connected to plus VCC, diode D1, base, emitter, collector, R3 resistor, capacitor C1 and capacitor C2, V2, C2 and E2. Here the circuit has two components. Both the transistors are NPN transistors, namely Q1 and Q2. Transistor Q1 acts as a switch in the circuit, and the transistor Q2 is fitted to act as an emitter follower. The diode D1 is present here for preventing the discharge of the capacitor C1 in the opposite way. The resistors R1 and R2 are present for biasing the transistor Q1 and keeping it turned on by default. From the start, the transistor Q1 is turned on because of biasing, and because of this, the capacitor C2 will be completely discharged through Q1, which in turn results in output voltage becoming zero. Since the transistor Q1 is on by default, to turn it off, a negative trigger of duration Ts is given to the gate of the transistor Q1. Yes, a negative trigger is given in this manner. Once the transistor Q1 enters into a high impedance state, the capacitor C1 is charged to a voltage VCC and will try to discharge itself. So a current I will be flowing through the resistor and the capacitor C2, and because of this, the current flow through the capacitor C2 charging and a voltage VC2 will appear across it. After the end of the trigger time, if the negative trigger given to the transistor Q1 is removed, then the transistor Q1 will enter into low impedance state by default and acts as a short circuit. Once again, the capacitor C2, which is in parallel with the transistor Q1, will discharge itself completely to have its terminal voltage drop shortly. So during the restoration time, the terminal voltage of the capacitor C2 will drop sharply to zero, and the same could happen for every time we given the input. So We will show it in terms of output. Since we are giving a negative voltage waveform, this is the trigger voltage. And for every trigger voltage, it's a negative trigger. So I have drawn it in the third quadrant. Yes. So how would be the value of VC2 is as soon as it receives it discharges through the capacitor C2 and then discharges, then charges again and then discharges. So this interval of time is called the storage time and this is the restoration time. Yes. So the capacitor will charge to a maximum of plus VCC. TS is the sweep time and TR is the restoration time. Hence, a negative pulse is capable of generating a sweep waveform in a bootstrap-based controller. A cross-coupled oscillator, another type of circuit called a cross-coupled oscillator. So previously we were using BJTs. Here we have used MOSFET by making a cross connection. And here we are using a FET. Yes, MOSFETs M1, M2, a third MOSFET, M3. The voltage is obtained across this LNC circuit. So two pairs of LNCs we have. So drain voltage. The coupled oscillators are oscillators connected in such a way that the energy can be transferred between them. This oscillator can operate in two regimes related to the DC value of the current which is flowing through the M3 called the tail current. Current limited regime and voltage limited regime. When M1 and M2 operate differentially, the common source of the transistors is virtually grounded. The total thermal noise produced between their drains and sources contribute to the output. This noise is converted to the excess phase and produces phase noise. The optimum phase noise occurs for I tail in boundary between current and voltage limited regime. Yes, to show this with a graph, the voltage amplitude, that is the tank voltage, the resonant voltage, S is taken across this, and the tail current in the x-axis. The current linearly increases with respect to and for up to maximum voltage it remains constant. So this maximum voltage For a quality factor of 10 and for a frequency of 1 gigahertz. The current, this is the current limited portion, and this is the voltage limited. Yes, this is the operation of a cross-coupled oscillator where I tail is in milliamps and voltage amplitude of the resonant tank circuit is in volts. Okay. This is about cross-coupled oscillator. Thank you.